In this presentation, I will talk to you about plane and rotary jacking and how we modeled it with DEM. So currently the mostly used foundation offshore is piles, and most piles are installed by driving. Now driving creates a lot of underwater noise, and that is harmful to marine life. There are some mitigation methods which are more and more applied, but they are not cheap and they are not ecological. So we need to find another way of installing piles. One way is using jacking, so simply applying a static force to have the pile installed at the required depths. However, the force necessary to install those piles is very high, same magnitude as the resistance of the pile that is expected. And this is due to two things: shearing along the external shaft and also the base tip resistance. This base tip resistance is intimately linked to the plugging of the pile, which can happen pretty quickly when you install them by jacking. So in general, there is not enough reaction force by the installation rig to actually install the pile at this required depth. One way of reducing this installation resistance is to use rotary jacking, so basically pushing and rotating a pile by applying some torque and force at the top. This has two effects. The first one is to rotate the shear stress acting on the shaft, the pile shaft, which will mechanically reduce the vertical component of it, hence the reaction force you need. Now, this rotary jacking may also affect the pile plugging, hence the tip resistance, and this is what I'm going to show you now. To do so, I will use discrete element modeling. This consists in modeling the soil sample by a set of rigid spheres which interact through contact laws, and they are free to move, hence to model large deformation. There are also those gray rings are some cylinders which are free to move radially, and they will simulate a constant stiffness, which enables us to reduce the computational time by truncating the sample size that is modeled. The piles are rigid, and we apply some rotation rate and vertical velocity rate, which we maintain this ratio PI, which is installation pitch, at a constant 10. If you want some more information about this, there is a paper in Computers and Geotechnics which has been published. Now let's have a look at the results. Plane jacking, if we simulate plane jacking, this is the blue line, we have almost 10 meganewton of vertical force necessary to install the pile at 8 meter depth. Now if we apply some rotary jacking, there is a reduction of 60% of this total reaction force. And this is due mainly to the base component. The base component is the largest component. It accounts for about half of the total resistance, and rotary jacking means that this is reduced by 70%. This reduction is intimately linked to the plug behavior. So this is the plug length. If the pile was fully coring, this is the dashed line, the length of the plug would be equal to the penetration depth of the pile. Anything that diverges from this line indicates some partial plugging at least, and when it becomes almost vertical, it's full plugging. You can see that for plane jacking, the plugging starts, or partial plugging starts, as early as 1 meter depth, while it is delayed in the case of rotary jacking. And at the end, both are partially plugged, but to different amounts. Now, if we have a look at the shaft external contribution, we can see that this was not the largest resistance of the pile, but still rotary jacking reduces it by 90% as expected. Now this comes at a cost, because as our shear stresses along the shaft are more and more inclined, then there is a torque that is necessary to install the pile while pushing and rotating. So a reduction in vertical force induces an increase in torque. Now, what is the mechanism that leads to those reduction in penetration resistance? If we look first at the plane jacking simulation, this is the state of the pile at the end of its installation. We can see that there is shearing along the shaft as expected, but also that there is some nose cone here, like some shielding and arching at the bottom of the pile. So arching is just the distributions of stress attracted by the rigid inclusion of the very rigid pile installed into the ground, and that creates some sort of shield that will deflect the soil on both sides of the pile during the installation. Now, if we look at those two phenomena are slightly different. So the plug takes some stress, some vertical stress, but the pile, the steel of the pile takes some normal stress. And they are not the same magnitude. If you look at it from the start of the simulation, when there is pure coring, to the end of the simulation where we have partial plugging, you can see that the ratio is very different. During the coring, the stress acting on the tip of the shaft is much higher, and it decreases, and at the end we have a ratio which is equal to about 15 or so. So still, even when we have partial plugging, the pile tip here takes much higher stress than the plug on the inside. Now, when we apply some rotary jacking, we can see that we have a totally different plug state. We still have some shearing on the outside, but we have a lot of shearing on the inside. There's a high disturbance of the plug. And at the bottom, there is much less shielding arching. We can't see this nose cone as in the previous case. Also, if we look at the ratio between the stress acting on the pile tip and the stress acting on the plug, it is much lower. So what's happening? What we assume is this continuous rotary jacking destabilizes the arching that takes place at the bottom of the pile. So there is much less of this shielding phenomenon happening, and it's easier for the soil to go into the pile. Now we can also calculate, thanks to the DEM, the radial stress profile inside the plug, which we have done in case of plane jacking and rotary jacking here. You can see that the rotary jacking has a higher radial stress, but still it has a lower internal side friction because of this rotation of the shear stress. So it is easier to actually enter, for the soil to enter the plug. Based on this information, we can also calculate a K value, which is the ratio of radial stress to vertical stress. It is in this case lower for rotary jacking, and we can use this information to do some plugging analysis of the pile, because most of the time we don't know what value to use. Now, if I just conclude this, what I can say is that rotary jacking has the potential to reduce the necessary reaction force by 60% in this case, through two main mechanisms. First, the rotation of shear stress along the shaft, and second, the change in plugging behavior. So rotary jacking creates some arching disruption and internal friction reduction, which makes the partial plugging, the coring of the pile, easier. Thank you.